Welcome back, everybody. This is part 4 in chapter 9, module 9, and now we're going to be comparing two variances. I want to make it clear, our standard deviation is here, standard deviation. If you remember, variance is actually our standard deviation squared. And we're going to conduct a hypothesis test of a claim about two population variances, not standard deviations, it's just going to be variance for what we're doing here. And this is going to introduce us to what's called an F distribution. So F distribution. A lot more complicated, and there are lots of tables, and I am going to teach this lesson in a way that we will not need the tables, although you certainly could do it that way. And here are some of the requirements. The two populations are independent. Two samples are simple random samples, and each of the two populations has to be normally distributed. If we don't know if that's normally distributed, then we can't run this test. And the test statistic for a hypothesis test with two variances is going to be, here's our F for F distribution here. It's going to be the variance of the larger variance divided by the smaller variance, and that's going to be our F score as we're looking at that. And the degrees of freedom for the numerator is n sub 1, so it's the number in the larger of the two variances, -1, and the denominator is the same. It's going to be a little bit easier to explain if I can show you an example. So let's take a look at this example here. And before we get started, the larger of the two variances is right here. So it says use these data with a 0.05 significance level to test the claim that men have body temperatures that vary, variance, more than the body temperature of women. And so this is going to be my 1, and this is going to be my 2, because it has the larger variance, standard deviation, but we'll turn it into a variance here. And let's start here. Our null hypothesis is that the two variances, two standard deviations, are the same. And the claim is that men, variance or standard deviation, is larger than women. And so let us, this is the claim. And you can see it's going to be a right tail. Now, an F distribution looks similar to a chi-squared distribution in the sense of it starts at 0 and it is skewed. And they give us, it's a right tail, they give us, this is 0.05. And we're not going to get the critical value. That's those tables I told you about, and I'd rather avoid those altogether. So we're just going to use p-value and the alpha to compare. All right, so let's find our test statistic. That's going to be F is S sub 1 squared, so that's 0.89 squared over 0.66 squared. That's going to give us 0.89 divided by 0.66 squared. So here's our test statistic, and I'm going to store that, just as a quick reminder, store into alpha A. That way I can use all of those digits here in just a moment. 1.818, and then I store it into A. Now, here's the thing. To get the p-value, we are going to go here. Let's do this. We are going to use FCDF. Show you what that looks like here. FCDF. And the lower in this case is going to be my A. because it's right-tailed, right? Off to infinity. Upper is going to be 99999, big number. The degrees of freedom of the numerator are going to be 10. Yep. 10. Degrees of freedom of the denominator, 58. There is our p-value. Oh, I didn't write it out. F, CDF. This is going to be 1.818, comma 99999. Degrees of freedom of the numerator were 10 and 30, 58, the denominator, which gives us 0.07739. The point is that is bigger than alpha. So if the p-value is bigger than alpha, then our conclusion is we're going to fail to reject. The null hypothesis, so there is not sufficient evidence to support claim that men's temperature is more than women's. No problem. And so what that's basically saying is that whatever this critical value is, we're over here, 1.8, with a p-value here of 0.077, we'll say, which is clearly larger. All right, and once again, just a label that is F graph. Let's do this now. Example 9, test the claim that those test background have creativity scores with a standard deviation not equal to the standard deviation for those tested with a blue background. Use 0.05 significance level. All right, so let us do a null hypothesis. And this is going to be here. And the claim is that they are not equal. All right, so we are drawing our F table here. And because it's not equal to, this is going to be a two-tail, which is going to cause some problems that I'll try to walk us through a little bit. So this is going to be 0.025, half of that. And over here is going to be the other half, 0.025. And because we don't know the critical values, again, we'll need an F table to get that. And you're welcome to use that if you wish. But what I'm going to do is I'm going to find F, my test statistic. And that is going to be, in this case, this is definitely the larger of the two. So F is 0.97 squared over 0.63 squared, which is going to give us 0.97 squared divided by 0.63 squared. There we are. I typed in the wrong number. It should be 0.97. 0.97 squared divided by 0.63 squared. There we go. All right, so this is 2.2 0.37, and again, I'll store that as A. Here's the problem. Because I don't know what these critical values are, if I do, in fact, let me do this. There are two scenarios here. One of them is that with the red, I don't know where this value is relative to here. So if it's over here, it's going to be 0 to there. So this is going to be FCDF 0 to my value, 2.37 with degrees of freedom. Right? Now, if it's this way, if it's like this, then 0 to there will work. If it's like this, if it's supposed to be over here, and then my p-value is there, and this one, the p-value will be over here. This is the 2.37. Here's my 2.37. So for this one, I would have to go FCDF 2.37 off to infinity, and so on. Here's the problem. I don't know which one it is, so I'm going to go ahead and start with this one. Now, here's the thing. Because it's two-tailed, when I'm done, I'm going to have to double that. And when I double that, if it's more than 1, which p-value can never be, then that's the wrong way. Let's try it out. So I'm going to go from 0 to there. So let's do FCDF. We're going to go from 0 to A. Degrees of freedom here is 34. Degrees of freedom here is 35. Paste. Ooh, that is the wrong way. That would be as if I did this and went backwards. Because you can see when I double that times 2, I'm way over 1, and p-value is never over 1, ever. It has to be between 0 and 1. Which means it's not this one. So let's try this one. So this is going to be CDF. And now we're going to go from A to a big number. Let's see what we get. Much more reasonable. Now we're going to double that times 2. So let's write down exactly what we just got here. So let's go back to our problem. Oops. So we got p-value is f of 2.37. Degrees of freedom 34. 99999. 34, 35. And then we have to times 2. What we got from that is this one here, 0.0129. And now we can make a judgment. This is definitely less than 0.05. So we're going to reject the null hypothesis. And I don't have enough room to write it all in here, but this is there is sufficient evidence to support the claim that the two standard deviations are not equal. So I'll add over here. And there is a comparison of two variances or standard deviations.